we? Here we go. Look at those green lines. We're done with that stuff. There's really these two big chunks of stuff we still want to cover in this course is these two big important things, right? PFC and fish and bonded particle modeling. But since I'm trying to develop this new course here, I'm doing a little experiment. And so what we're going to do here is we're going to continue with this hands-on thing where we're doing the odometer test, and then we're going to screw around and glue that stuff together, right? We're going to be just like Peter Kundal in 1994 when he had this idea and said, what if I put some glue on here and see what it does? Oh my God, it looks like a rock. And we're going to do this in a progressive way. We're going to start with the simplest possible idea of glue, which is the contact bond. So I'm going to introduce that. It's a very simple addition to the linear model, and then we're going to play with that and see what happens. And then we'll go and say, hey, this has some limitations. It's only like a certain type of rock. It's not like general rock. So what if we have a parallel bond? And we'll talk about that. We're not going to get through all this today. But then we'll talk about the flat joint, which is yet another there's been an evolution of these models. And so we're going to talk about them in this sort of basic overview way, instead of just giving some big giant lecture about this, because I think this will lead you through the thinking of what underlies these models. And you'll be learning how to do stuff. And you will do a little bit of fish along the way, and then we'll do a formal discussion about fish next time. Okay? So again, instead of just doing these formal talks, we're going to actually try to work our way through it and get to and kind of just naturally absorb it. Okay? We on board? Give me a yes. Yes? Good?
That's good.
Yes.
Okay, excellent. Here we go. Gravity packing. Remember, particle cloud, let it fall, fills the box. That's what we worked on, right? Very small, 20 lines of code to do this. And then we did a little bit of work where we said, now we can identify layers by using groups. And then we can color the layers, and we can give properties to the different layers, lower, upper, bottom, etc. And so that gave us a sort of an idea of this. And this is a granular system, so we use the linear contact model. And now we're going to modify that a little bit so that we can do an odometer test. And again, an odometer test, there you go. That's Ayot's hand. You can see the length scale here. And so, right, it's filled with particles. In reality, it's pushed down. We measure the force on the platen, and we turn that into stress. And we measure the displacement of the platen, and we turn that into strain. And then we can plot this, right? And so here you see loading. It's taking more and more stress. There's a time dependency here where they actually hold the platen, don't let it move, keep the stress constant. And you can see it continues to move a little. And then we unload, and your stress goes down, comes to here, right? We're not going to talk about time dependence. We're just going to try to create this curve, right? Load it up and then unload it. So we're going to move it down, and then we're going to move it back, right? And we're going to measure this, right? So this curve is an emergent response of the model. And then we're going to talk about, why does this thing stiffen? Why doesn't it just go straight up? But let's get there first, okay? And we're not going to create a cylinder shape. We're just going to use, and we're going to do it in 2D like we've been doing, okay? Because all the ideas are the same in 2D and 3D, okay? So let's go back to this tutorial here and continue to work with this. So here we go, set up this thing. We started with the gravity pack, and I essentially copied that, and now I'm adding a little bit on top of that. And we also talked about, so now we're doing two steps, right? So we're going to have an outer level data file, do all, and when you call this, this is going to be the starting point of the whole entire process, right? So you can see what it's going to do. It's going to create a gravity packed system. It's going to save that as a save file. And then we're going to perform an odometer test on it. So we're going to have to do a few other things, right? And we also talked about we're going to parameterize this system so that we're going to end up having some key parameters, right? So that then we can just change these parameters and the system we can change the system, right? And so here's what we've got so far, right? The width and the height of the box. We're going to use a uniform distribution of particles. There's the sizes. And then we're going to have to move that thing down at some velocity, right? And these are fish variables. And these are global fish variables. Global is a programming term. It means that once you create that variable, it can be accessed from anywhere. Any function can use it, okay? All right, everything, we all on board here? Makes sense?
Yeah.
Okay. So let's try to, let's work through this and then finish that odometer test, right? So gravity pack. This is what I do all the time because you can never remember what I've done in the past. You have to refresh yourself. So gravity pack, let's go to that one right over here. Double click. Here's this data file, fits on one screen. Let's just walk through this again. Create a cloud of particles above a box. Allow it to settle under gravity until it's stable and doesn't move anymore, right? So new, we're starting a whole new model. Now we're calling in this myparameters.dat. What that means is PFC gets to this line, and then it suddenly goes to this file and processes these lines. So after it's done doing this, these global variables exist. And actually, it should be global as well to be proper. So we go back here. Now those global variables exist, right? So if I just hit return, if I run this thing, and if I say list fish, look at that. Those are the fish variables that currently exist in the model. There's 5 of them. They should be 5 of them here, right? And there's the value that they have, which are the values we assigned. And also they have fish variables have a type. They can be an integer or they could be a floating point number. What's a floating point number? That's a computer programming term. I think we all know what an integer is. It's a discrete thing. Goes from negative infinity to positive infinity, and it's just it's an integer, right? 1, 6, 5. Floating point number is mathematically what we call a real number, right? It has infinite things, right? If you take 1 divided by 3, you actually get a number that's 0.333 forever. We can't represent that on a computer. We use floating point arithmetic, and that basically means that we decide how much digits we can deal with, because the more digits, the more memory you need. And that's what we call a floating point number. So you can just think of it as that's a number. Like here we go. It's a real number. So I can put in like 0.02. Okay. And there's other types in fish as well, but those are the main things, right? And this isn't any kind of computer program. We have integers. Think about integer. It's unambiguous. If the integer is 6, the integer is 6, and we can store that and we know what it is. If the integer is the result of 1 divided by 3, we can't store that actually. And theoretically, we don't have that number. We have an approximation at some level of precision of 0.333. Okay. So there's the fish variables. Look at over here, way over here, upper right corner, there's a little symbol, looks like a fish. If I click on it, and I'm sorry, I can't make this bigger, but it's telling us the same stuff as down here, right? So here you go, name, value, type. And also we might have a fish function. That would be there. So for example, fish, define, hello. io.out. Oh, what are we going to say? Here we go. Hello world. Famous hello world. And now if I run this thing and call this in, let's look what we got. Gravity pack. It's just going to call in the parameters. Boom. Now I go over here. Oh, look, hello, value 0, integer. Okay, it's a function, right? Do the same thing here, list fish. So now I have a function that exists. Function's called hello. It's a function, so I can execute it. So to execute a fish function at the command line, I have to enclose it in square brackets. So I sit there and I can now say, hello, let me make this bigger so we can see it better. I think it's called console. And I think I can change it by select font. Let's make the font 14. There, is that there? But now I think we can see things better, right? So now if I run hello, this is invoking the fish function. So hello in brackets, hey, look at that. Hello world, it printed it out. And because it's a function, it always returns a value. And so in this case, by default, it's going to return an integer value of 0. Okay, does that make sense? I just create a fish function. I can do anything in a fish function. Right there, I invoke the fish function. Basically, Shihang wrote a very extensive set of fish functions to create a new program that does his crazy whatever those thing, ECFM thing and whatever. That's actually a program. You created a completely novel program with a novel idea, and the way you did it all was using PFC and using this language in PFC to be able to generalize this thing. You also are running a different code too. But this is the idea, right? This is why PFC is so general. And the fish language is, in the world of computer programming, there's certain, you could talk about a language being like fully complete. This is a fully complete language. This is as powerful as C++ or Fortran or BASIC or anything. It's a full-blown computer language. So therefore, anything you can do in a computer program, you can do with fish. Okay. So enough said. And fish is like Python in many ways. So new, call in those. So now we have those fish variables. So let's go back there and get rid of the hello world business. Delete. Here we go, large strain. We're running this in large strain. We almost always do with PFC. That means the particles can move however they want. Setting a random number seed, giving it a title, right? We made a domain. We're using the famous contact model assignment table. Here we go. Everybody is going to have the linear model, all contacts, and they're going to have values of Kn, Ks, and friction coefficient. That's the only thing the model has as parameters. Here we go. Generate a box with the wall generate command. Here we're using the parameters, right, to figure out where to put that box. And then we're deleting the top facet. And we named the box MV. So then what it'll do is it'll make 4 facets called MV top, MV right. If I run this, look at it, there's my walls. There you see over here, bottom, left, right. So that's what's going on there. Here we go, generate the cloud of particles with the generate command. Boom. Whoops, I just wanted to say return there. Run it again. What do we got? Boom. Whoops, that's not right. Oh, I went too far. Here we go. Ball generate. Fewer balls were generated. There we go. And the generate command is very limited. You almost never use it. But it's going to generate, it's going to keep randomly taking balls and trying to throw them in here so they don't overlap. And this is the best it could do because they can't overlap. So that's what we get. And it's just a uniform distribution. Okay. Normally, we talked about this before. We use the distribute command, and then you can actually specify a completely general size distribution. However, the balls will overlap then, and so you have to let them rearrange in things when you do that. Okay. So here we go. Is everybody with me here? Yes, yes. This should all be simple.
Yes.
At this point.
Yes.
This should be quite straightforward, right? We have to give balls, we somehow have to give them mass because we believe what Isaac Newton told us, that F equals ma, so there has to be m. So the balls are going to get a density. Remember, we don't give a mass in PFC. We give a density, and then based on the size and the shape of the ball, we figure out its volume. And then we hit the density times the volume to get the mass. We give a damping. We're using local damping with a high coefficient, 0.7. That will allow us to have a quasi-static type system. We turn on gravity. We're on Earth, so we're going to use this. All the units are SI units. I should have said that here. Oh, I did. Okay, SI units. That means gravity, meters per second squared. And then we're going to use this solve ratio average command, which is going to continue to cycle until the ratio of basically of the unbalanced force on a particle relative to the other forces is small. And we find that a ratio of e to the minus 5 seems to be pretty good for our systems, and we're pretty much at close enough to static equilibrium, right? So we run this guy, we look at it. It's always nice to look at the force chains. Those are critically important things that tell us about the fundamental behavior of granular systems. They're all shaking around because it's still readjusting. And again, we talked about this. This is a frictional material. It's a sand pile. Sand piles take a long time to come to equilibrium. If we start deleting parts of it, if I delete one guy down here, the whole entire pile is going to rearrange. So that's just the behavior of the system, right? And so now we've got a save file. There we go. Save. So we're done with this. And now in the do all, we got that. Now we're going to go to odometer test. And the first thing we're going to do is restore that state. So now we're exactly where we were before. And we're going to change the title. So it says odometer test. So let's take return. Let's run this. Let's take a look. Hey, here it is, odometer test. Okay. So now we're going to make a wall at the top. And we're going to call that a platen. And so we're going to use the wall create command. We're going to call the wall platen. And that command requires the keyword vertices, and it only needs 2 points in 2D space. So to make that clear, a point in space is not a floating point number. It's what we call a vector. And so if I hit return, I'm creating a new fish variable called point A that is of type vector. So what's a vector? A vector is 2 floating point numbers in PFC2D. So if I run this, and now if I say list fish, I've got, where is it? Point A, vector 2. That means it's a vector with 2 components, and they're both floating point numbers. Okay. You're going to find out there's all kinds of types in fish, but a vector is a very useful thing. So now we got those 2 values, and now we can do the wall create command because we're going to feed them in. So if I run it, it tells me green is your friend. Green means information. If this came out in red, that means error. If it's an error, it'll tell you, it'll stop the execution, and it'll also typically put a box up here that'll say whatever. What if I say create T? I spell it wrong. Now I run it. Now here we go. Look out, red, bad conversion, da 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 da. Okay. So create, there's my wall. So if I run this, let's look at the system. Hey, that's good. And I just made it at the top. And so let's just go. We could have screwed around. We could have actually, at this point, we could have written a fish function to figure out where the topmost ball is. Right? So we could have looped through all the balls. We could have taken its position and then take the biggest of all. So then we could have known this height, and then we could have done the create. We could have made this platen wall really close. But we're not going to screw around with that. We're just going to put it there because that's easy. It's always going to go at the top. And now we simply give this guy a velocity, and that's the wall attribute. Walls have all kinds of attributes. If I say wall attribute, it's wall list attribute. And so there's all these different things, the moments, the rotation, the spin. This is basically the properties of the wall. You're telling it what to do. You give it a velocity, for example. So there you go. And I'm just going to give a y component of velocity. So if I do this and I'm doing it, notice I'm using the range. If I don't use the range and I give this command, it's going to, y velocity was initialized in all 4 walls, right? There's 4 walls here, 1, 2, 3, 4. There they are. and it's doing it to all of them, but I don't want that. In fact, let's just run it. Now, if I run it, the whole system, right? They all have that velocity. So it ends up doing that. That's not what we want. So we shift escape, I think, to stop this thing. Yes. So we're going to use the range, and this is the way we tell it, range set name, and here's the name, platen, because that's what we called it. We called that wall, we named it. So if we're lucky, this is only going to apply. So it says y velocity initialized in one wall. That means it probably worked. We gave it this value of pvel. Notice this. Got to be careful here. Pvel, here's my definition of what the heck I mean by that. Platen velocity, but notice I say positive number, because now when I implement this, I'm assuming it's a positive number. And so that means when I assign the y velocity, the velocity component in the y direction to the top wall, I have to give it a negative value. So I can say negative of whatever this is. That's why I say negative right there. There's a negative pvel, okay? Let's also look at this. I can say wall list attribute velocity, and we're going to see all the walls and all the velocities, and everything's 0 by default. So all these walls originally have they're not moving. And you can see it looks like it worked because it only did the platen wall, and it's just the y component, right? And so now we can, for example, cycle 7,000, and if we run this thing, there we go. And we haven't talked about anything about velocity or anything. I just screwed around and gave it the number that I did. And remember, PFC is computing a time step. You can't change that because that has to be done in order to properly integrate F equals ma. We know F equals ma, so we have to figure out what the velocity is, so we got to integrate it. To do that, we do finite differences, we discretize the system of equations, and when we do that, we need a time step. And that time step is related to the mass and stiffness of the overall system. And PFC is constantly checking that and applying that. So the time step may be changing. So what this means is if we give a velocity, it's just going to, the amount that it moves is going to be velocity times time step. That's going to be the motion during one step of that wall. And so it's not, so like the question like of how many cycles do I have to apply to make it go and just about reach it? That's not something I can directly figure out, right? And so I just screwed around here, and given that this was the time step, I know that if I take like 7,000, I'm getting close, okay? We could have this is what I noted in, make it cycle until a specified displacement has been achieved. And there's a way to do that. I don't know if any of you maybe tried to do this. Basically, there's a command called model solve. So remember, model solve, and we said ratio average, 1e minus 5. That's one of the things you can do with solve. There's many things you can do with solve. Solve means continue to take cycles until some criteria is met. And so the most general criteria is to say, oh, it's a fish function that I have to create, and every time that fish function gets called after every cycle, and my fish function decides, is my criteria met? If it is, return true. If it's not, return false. Connected there. You guys still all there? You guys still all there?
Yes. Yes.
Okay, good. So we're not going to do this. Did anyone try to do this? Yes? No? No? Okay.
I'm using that because you taught me how to use it.
Oh, okay. So you did it.
Yeah.
Okay, excellent. So you should do this. And we're not going to do it because we're just going to screw around here and do the 7,000. Okay. But basically, this would be a way you would be able to control how much displacement you want to apply. Because if you remember in the test, that's what we're applying here is displacement. Like in the test, it says, and I assume AI, you run these tests, you must have some kind of fancy equipment for the loading frame. And do you tell it how much displacement to apply? Is that how it works?
So we apply on the strain control test. So yes, we tell it the rate that we want to deform or apply the displacement and basically.
Okay, so you tell the machine, I want to apply 0.1% strain, and you
Yes.
also tell it how fast to move that thing.
So
right?
the machine itself doesn't operate on strain stress, it's force displacement. So we apply displacement over seconds. We convert that, like get the calculation that we need, and then we apply that in how many inches per second we want to deform the sample, basically.
Got it. So this is kind of like what we're doing here. We're giving a velocity in meters per
Yes.
second.
Yes.
So, okay, so we're doing the same thing as is happening in your test. Got
Yes.
it. Because that's what we're doing, because there you go. That's the Y value of the velocity. That's what it keeps doing. And by default, PFC is running in what we call fully dynamic mode. So it really is meters per second. The time is meters per second. The time step is seconds. Okay, so we kind of have what we need at this point, because what have we got now, right? We have our vessel and we have our platen, and we're telling it to move, okay? So we've basically built an odometer here, and we've got the ability to fill it with particles, right? So now we want to build the monitoring stuff the things we want to monitor, right? So the goal is this guy, to make this curve, stress versus strain. So let's first look at, what if we look at the force that thing is pushing with? How are we going to get the force that the platen is feeling in PFC? How do we get the force? Wall list attribute. One of them says force dash contact. Wall list attribute force dash contact. Look at that. Here we go. This is the platen. This is the current force that's the result of all the particles pushing against the wall. That's what this is. And so you can see the Y value, there it is, 3.9 e to the 4. There's a much 10 times smaller Y value acting on that thing. Okay. So we can, let's get rid of these things. So let's first just do that. Let's just ask the wall what the current force is. Okay. And then let's use the history mechanism to plot that. So we're going to be able to make a plot of force versus step number. Okay. So let's say if we can do this. So let's go here and let's just make a save file. Save, I'll just call it, what did we say? Model save almost .p2 save. So if we do this and run it, what I want to do is, as we're screwing around developing this, I want to be able to just restore so we don't have to sit here and wait for this thing, right? Well, actually, that's not what I want to do. Sorry, we're just going to do that. Okay, here we go. So we have to create, what do we have to do? We can use the wall history command. So we're taking a history of some of the things in the wall. If I hit wall history F1, here's the wall. These are the different things that I can ask the wall to monitor. And one of them is force contact Y. It's the Y component of the contact force. And it's the sum of all the, it's the force produced by the sum of all the things pushing against the wall. So wall history, what is it? Force dash contact dash Y. First, I'm going to get history and name. And let's call it plat F, or platen force. Because our wall is, we're thinking of our wall as a platen, right? And then I can say force contact Y. And I gotta then tell it this wall history block. I gotta say which wall. Record the history of the wall with name S. So the keyword is name, and then I put it in. So I'm gonna say name, and the wall name is platen. Remember, wall create up here, platen. So let's see if this worked. Let's run it again. We just have to be a little patient here. Actually, no, I don't need to do that. I'm actually going to do this before I move the wall. Just a second. I want to move this to the end of this thing just to get it out of the way. Okay, good enough. Cycle 7,000, but we don't have to do that. We can just first, let's see if this history command worked. Wall history name. I'm going to run it. Going to try to run. Here we go. So created history. It looks like it worked. Let's look at history list. There, history is called plat F, and there we go. It's what we want. It's the wall contact force of wall 5. And if I say wall list, I can see the name. So each wall also has an integer associated, a unique one, and it also has a name. So it looked like that worked. Now we need to hook this in to the history mechanism. So we're going to say, first of all, history end step 1. That means sample the histories every single time step. And so history, do this. Do we say, I think we say it's a wall history. No. Oh, we've already got it. Hang on, I don't have to do anything else. Let's just do that. So every step, sample this. Now the history exists. Now do 7,000 steps. Let's run it. Now it's running. After it's run here, let's then go and create a history plot item. Okay, so let's see if it worked. So what we're going to do is make a new view, a new plot. So we just can plot the history in a different window. So how do I do that? I go to plots. No, that's not how I do it. How do I do? I think I can. If I go to plots, give it the right finger, new. So I'm making a new plot. Give it a name. Call it force disp. This is going to be my force displacement plot. So there's nothing in it. So I'm going to go to the checkbox and click title, apply. Now I can see my title. I also always like to have the number of time steps up here. So I'm going to go into legend and say step. There we go. And now it's a history. So right here, plus, it's called history chart. Boom. There we go. And here we see all the possible histories. Remember when I did list history? There's only one. Click. And there we go. By default, it's plotting the value of the history. And our history is named plat F versus step. So notice nothing happened. And then it started building up, right? And actually, while we're developing this, let's go and add it to this plot item because I want to see it on top of the system for now. So history chart, do the same thing. There we go. All right. So there's our system. There's our thing. Now, And of course, if we watch this, right, nothing, it's going to be 0, 0, 0 until it starts to touch, right? And we could see that as we're running it, okay? But we don't want to plot versus step. We want to plot versus amount of motion that the wall has had, the applied displacement, right? So how are we going to do that? Any ideas? What if we look at the history again of a wall history, and one of the other things we can monitor is displacement. So displacement in the Y, accumulated displacement, right? So let's do that. Let's hook up another history that's going to monitor the Y displacement of that particular wall. So there we go. Here we go. Right after that, wall history. And let's call this one flattened disc. Flattened displacement. And what's the name? Displacement.y. Displacement.y. And which wall? It's the platen wall. Let's do return. Let's run it. There we go. History list. There it is. Notice how I'm doing everything step by step. Making sure it works as I go. There we go. Now let's run this guy. Here's my view. Oh, watch. We're going to get to see the force start to build up. So far, we're just plotting down over here, the left, platen force versus step. So when it comes into contact, you see the contact force chains, boom, and you can see it's getting bigger and bigger because the guys don't have anywhere to go to get out of the way. Okay, so how do I change this history now? How do I make this axis be the displacement? Over here, Shihong, how do I do it? Guys there?
Yeah. Sorry.
How do I do it, Shihong?
Oh,
With this history.
We need just name wait. So what? Okay, what's the question, please?
Oh, the x-axis. We want this x-axis to be displacement, not step.
Okay. For me, I just write type the ID, the name, plot displace.
Yes, so here, so the plot item has here's the series, that's the y-axis, platen force, versus, that's what VS means. So I want to, there's another history that I want to be monitored for the x-axis, and that's the displacement. So it's called plat disp. So I'm going to type that in, plat. So I'm telling the plot item to do that. Notice over here, it's plotting platen force versus platen displacement. Okay, and it looks weird because the platen displacement is negative. It keeps getting more and more negative because it said this is the, what is it? The y component of the accumulated displacement. So this wall, right? This wall is moving down, so the displacement is negative y. So the displacement value, we keep sampling, keeps getting more and more negative, right? So it's plotting that. Remember, zero force, now it starts building up. Well, we don't want to see it this way. We would rather make this reverse the direction of this value so we can look at like the way we typically look at these plots. So in the history plot, we can do that. Here we go, versus platen displacement, and there's a thing called reverse. If I click reverse, now we're happy. Notice here it's saying it's plotting versus the minus of what it's monitoring, right? So now basically we've defined in our plot, we've defined positive x-axis as actually compressing the material, moving down, okay? Another thing that's helpful here is we would like this x-axis to start at 0. And it's not exactly starting at 0. It's starting at the very first history that we sampled. And it didn't sample it till the wall had already moved. So here I can go axis 1, and I can say, it says minimum and maximum, and now it's automatic. So I uncheck automatic and I put 0. Here we go, 0, right? Okay. And I could probably do that for the y-axis, but I don't really have to, but I will. There, 0. That's what we want it to start at, right? And of course, now I can label this thing, right? So this is platen force. I'm not going to do it, but I could create labels here, right? So now we have, let's actually make a label because this is important. So I'm going to say platen displacement. We should always have units on our plots, so it's in meters. And what is this? The y-axis is platen force. What's the units? What's the units? What's the units of force?
Newtons?
Exactly, because we're using SI units for everything. So therefore, that's because we're putting in properties using SI units. So therefore, a force has to come out as newtons. My headphones keep cutting out. Everyone still with me? Am I back?
Yes.
Yes.
Okay, good, good, good. Okay, platen force, platen displacement. We're getting there. This is our goal. We actually want to have platen stress. So let's see if we can figure out how to turn that force into a stress. So theoretically, what do I have to do to turn the force into a stress?
Divide by area.
Exactly. Divide by area. Now, what's the area of this system?
The length.
It's the
of
length, which we're calling width. So we have a fish variable already that knows that. And what else? Because area is, it's two things. It's something times something. And what do we multiply this thing by for the 2D model?
Why?
It's 1 because the thickness is the out of plane direction. And if you recall, for a 2D model, these are actually unit thickness cylinders all lined up. So to turn that into a stress, there we go. We got to do that. So to do that now, there is no way. Like, for example, the wall does not have the history. It doesn't know about stress. Okay, it doesn't have a stress here. And if you think about it, it's impossible to have a stress there because how the heck is it going to know what to divide by? I mean, how's it going to know how big the wall is and stuff? So that's going to have to be done with fish. So what are we going to do? We're going to create a fish function that is going to ask for the value of the force, and then it's going to divide it by the width times the thickness, and it's going to return that value. And that fish function, every time we call it then, is going to return the axial stress, the platen stress. And then we're going to hook that in to the history mechanism. Okay, you see the picture here? So fish define, and let's call it sig y. Sigma is a typical symbol for stress. And so what am I going to do? I'm putting in a comment here, sigma y, axial stress. Let's just say, yeah, let's just call this axial stress. And now what's the unit? And let's make it so that positive is compressing. Okay. So sigma y, let's just pretend, let's just check this out. So I'm going to say sigma y, I'm going to return, when I call the function, it's going to return a value of 42. Let's see what happens here. Function, list fish. I should have a function in there called sigma y. So again, to invoke a fish thing, I got to put the square brackets, and now I just call sigma y. It should, what's it going to do? It's going to return a value of 42. Okay. So let's just leave it like that, and let's hook this in to the history mechanism. So, and this is not a wall history, it's a fish history. So fish history. What's the name of this history? Let's call it Let's call it sigma y. And let's, just to be clear, let's call it my sigma y. Because otherwise it's confusing. If we give the name here the same as the name of the fish function, it's going to be hard perhaps for you guys to follow this. So here we go. We're going to make a history called my sigma y. And what's it do? It's fish history. So now we have to say which fish function should it use. So if I set fish history, here we go, symbol. Create a history of the fish variable called symbol. And this is the history name. So fish history name, that's what I got. And the fish symbol is called sig y. Sig y. Let's return this. Let's see if this part so far works. Created history, my sig y. History list, my sig y, fish function. So now we got 3 fish functions hooked in there. Platen force, platen displacement, and my sig y. Let's actually call this platen sig y. That's actually a better name. So history list, whoops, plat sig y. Now we should have 3 fish variables. Sorry, history list. Force, platen displacement, platen sigma y. That's what we want. So now let's just run this thing. Okay, so let's run this thing. And now we've got that history hooked in. So it's going to sample that every time. It's always going to give 42, but we're just testing this. So let's look at the view here. There's my force displacement, platen force, platen displacement. Let's turn off the walls and balls. So let's just first make another history plot. Turn off the previous one. There's our new one. And we have this thing called sig y, plat sig y plus. And so notice versus step, it's a new history, and it's 42. So that's good. That means our function, everything's hooked up right. We've got a function, it's getting called. We're all happy, okay? And we're going to want to plot this versus the same thing we did before. We're going to want to plot it versus platen displacement. So here's that history versus plat disp. And so now we've got versus plat disp. Okay, and we want, and we're going to reverse that. And so now we've got just like this, platen displacement, but instead of platen force, we now have this platen sigma y, but it's 42. So let's go and make it what we want it to be. We simply now have to just write that function inside. Everybody with me?
Yes.
Okay.
Yes.
Okay. Cool. Function. And don't worry, we'll take a break in a minute here, a little bit. We're almost done. Sigma y, holy smokes. Okay, so what we want to return, just a second. Here's how I would write a function. This is how you should write functions for things like this. This is actually a function, returns a value. So here's the value. I don't know, I'm coming with the name. The output sigma y, it's a local variable. Somehow I'm going to do something and get it, and then when I've got it, I'm going to say return out sig y. Okay? And now I have to figure out what out sig y is. So let's see. Out sig y equals wall dash, what the heck is it called? Just a second. I'm trying to hit F1. So in the world of fish, we have complete access to all the internal state information in the model. And if you recall, a PFC model is a very simple thing. It has particles and it has walls and it has contacts. So now we want information about walls. So here it says walls, fish functions. And what we want is the wall contact forces. And so that should be force. Where is it? Force dash contact. Get the sum of all contact forces acting on a wall. The resultant force is expressed in the global coordinate system. So here's the function name, wall.force.contact. It returns a vector, a force vector. So in this case, it's going to return a vector of 2 floating point numbers. Okay? And we're going to want the y component of that. Okay? And so This is a function, but it has a parameter because we're asking for the total force on the wall, but it needs to know which wall. So we have to tell it in the parameter list which wall. And so we have this thing we call a wall pointer. What that means is in the world of computer programming, the way you refer to things, to variables, to well, let's call it things. The way you refer to things is that you have the memory address of where they are. And we call this a pointer. Okay, so we're going to have to get the pointer to the wall named Platen. So now we also are going to have to figure out how to get that. So just a minute here. I'm going to duplicate this screen, this tab. And now I'm going to say there's one called wall.find. And what this returns, so this one, when I call this function, I give it the name of the wall as a string. So here I can put wall.find Platen, and that returns to me the pointer to that wall, which I then can feed into this function to get what I want. Okay? So let's see if we can do all of that. So I'm going to say, clear, local, wall pointer equals what? Wall.find, and I called Platen. And let's actually see if this is going to work. I'm going to copy this. I'm going to go to the PFC command prompt and put my square brackets, paste that in there. And did it work? A second. No, yeah, wait. Okay. It did. So this function, when I ran this in Fish, it returned a pointer to a wall, and I'm listing it. And this is wall 5. Here, let's just do it in here. So that's the pointer. And now I need to call the function, the one that's called wall.force.contact. So wall.force.contact, which wall? It's the one that's called Platen. That's the pointer to it. So that's going to give me the force. That's the same thing if I were to say wall attribute list, wall attribute list contact dash force. Oh, come on. It's wall list, sorry. Wall list attribute contact dash force. Come on. F3. Oh, come on, help me. I'm doing the wrong command here somehow. Oh, it's called force dash contact. Okay, wall list. This is what I'm actually going to try to query. Wall list, but I want to just see attribute force contact. There, this is the force acting on the wall called Platen. There it is. So this second component is the one we want. And we're getting it here, up here in this Fish function. So that should be the force. And then I'm going to divide that by what? I'm going to divide it by our Fish variable, which is called, is it width? Yeah, width of the box. It's called width. So I'm going to divide it by what? Width times 1. Okay, and I put a comment on there. It's always good to do this, just to put that in there, because now it's clear. It's an area. So it's got to be two things multiplied together. Okay. So this, when we call this function, this should give us that thing, right? Let's actually test this before we screw around with the history. So here we go. I'm going to run this. I'm going to define the function, and then I'm simply going to cycle until I'm pushing it, and then I'm going to call the function. And we're going to see, is it returning the same thing as when I ask the wall here with the list? It should be, to know if it's working. Okay, so let's run it. And look at my view. There we go. It's pushing. Now, there should be a function called sig y in here. So I'm going to call the function by putting it in square brackets. And it returned, it returned a vector, remember? Because wall.force.contact returns a vector. So it should have returned the x and y values in those two slots of a vector. So let's see, what are the values? Wall list attribute force-contact. And so these numbers, so the x, 3.04 E3, got it. Y, 3.94 E4, got it. Okay. So is everybody with me? I now have my function. Okay.
Okay.
Yeah.
Cool. Now, history. There it is, fish history. Right there. That's the function. So every time, every step now, I make the history sample itself. So this history gets sampled, and what it does is it's a fish history, which means it simply calls this fish function, and whatever that returns, that's what the result of the sample is. Okay? And so this now is always going to give different values because it's always going to go and, find that wall and ask for its force. So let's see. Let's see. Fish symbol, sig y. Let's run it again. What did it not like? Ha! Tell me what this means. Look at that. It says the fish symbol sigma y that's being used in the history, which we named plat sig y, return value. It's returning a value, but it's not able to convert it to a single real. What does that mean? What's the problem here? It's a vector. The history mechanism can only sample floating point numbers. That's it. It's not fancy enough to sample vectors. So what I need to do is make this function right here just return the y component of the vector. And so the way I can do that is I got this local vector called out sig y. I'm going to do this. So if I say out sig y 2, it should be 1 would be the x component, 2 would be the y component. Let's see if this works. Hey, it was smart enough. Maybe it didn't choke on that. Let's look now. Well, first, let's just call that function sig y. See what we get back. Well, look, we're only getting one value. So you're with me here. It's a vector. We're just taking the y component. Okay, so now the history should have worked. And so let's see. Turn all this junk off here. History. Okay, platen, sigma y. It's giving me a value. Right now, the value should be 3.9 E4. 3.9 E4. I think it's working. So let's go back. So this is it now. It's the axial stress versus the displacement. But we want to plot it versus strain. Okay. So now we also have to do the same thing to have a fish variable that's going to return the strain. Okay. So we'll do this, we'll get this plot working, and then we'll take a break. So just like we had a fish variable to give us the stress, fish define, and let's call this one epsilon y. Again, we typically use the symbol epsilon to represent strain. Okay, so fish define, local out eps y, return out ep y. This local here means that inside the function, this variable exists and can be set and you can do stuff with it. But when the function is done, this variable no longer exists. So it means it's just local to this function. It's not globally accessible. General good programming practice is to minimize the number of global variables. Because like this thing doesn't mean anything to the rest of the world. It's only something that's temporarily needed to do this computation. So you'd like to try to minimize the amount of global things. So epsilon y. So now we're going to have to take what? We're going to have to take the amount of displacement of that wall, and we're going to divide that by something. So let's say out F equals wall dot, I don't know. Let's see. Go back up to here, wall dot force contact F1. Let's look at, there it is. Let's look at the other. Is there a displacement here? And there is. Get set the wall displacement. Notice it says get set. So what we want to do is get the value. That means it's on the right-hand side of an equal sign because we're getting the value and we're assigning it to the V, which is the thing that comes back out. Okay, it's the return thing. If we put it on the left-hand side of an equal, we can actually give it a displacement. So what's displacement in the world of PFC? Every particle and wall will have associated with it a vector, which is what we call its displacement. And what happens is every time step, that vector gets incremented by the incremental displacement that just occurred. It takes the velocity of the particle times delta t and it adds it to this value. And so we can then use that. So we might have a model running at some point, and then we might say, let's set the displacement to 0, and then now let's start monitoring it. Okay. In this case, we created the wall, so the displacement is 0 anyways, and now we're just using it right away. So we don't have to set it. So let's see if we can write this code. Wall dot displacement. And now I'll just do it the same way. Wall pointer, and this is local, so WP, it only exists in here. The fact that I use the same name here doesn't matter. So wall pointer divided by length. Change in length divided by length, that's the strain, right? And we're monitoring strain, we're doing it with respect to the length. So we're actually, you know, so by the time it gets to here, there's going to be a lot of strain, okay? So let's go back. Now, is this going to work? Wall displacement, what's it returning? Going to have the same issue as before. It's returning a vector, right? Because it's a displacement in the x and y. So we're going to have to do the same thing here. We just want to return the y displacement. That's what I put the 2 here. Okay. And so then we hook it into the history mechanism. And let's call this Platen Fy. And that is the fish function called Fy. Fy. So let's see if this is on. Okay, Why is this not working? See, this is what always happens in the real when you write code. Help me. You cannot create a new.
I guess it's height, not length.
Okay. Let's look at the parameters. Height of box, that's true. That's not what caused the problem. Well, let's run that. Whoa, the heck, how come it worked that time? That shouldn't have mattered. Maybe I spelled length wrong or something. Okay, call it right now. Out Fy, let's see what it is. Okay. Negative because the y displacement is negative, so it's returned. This is a negative strain. Negative 0.45. Let's look at the history. The history at this point, if we plot the history called plat Fy, it should be this value. Let's see. So go back to the view and go back to the history, and let's just, for now, let's just make that a new history to see what it is. Let's turn these guys off. History. Here it is, Fy. Flat XY. Okay, is this making sense? Step number is whatever, 8,000, and then it went up to 15,000, and started at 0, the plat XY, and now it's been getting more negative, and now it's about minus 4.5, e to the negative 1. So it's probably working. Okay. We good? Make sense? Okay.
Yes.
Yes. Okay, check it out. Now we got all the essential needs. Here we go. Now we're plotting force versus displacement. Let's change it. So, going to just change this existing history. So look, it's series is Platen force versus Platen displacement. Let's go and click this X. Now it doesn't have a series. So let's choose sigma Y versus this thing called plat XY. Plat XY. Boom. And why is it not showing me this? So this is now axial stress. Once we get it to work, what are the units?
MPa.
So actually pascals, let's put just newtons per square meter. That's the word, and I put it on the wrong axis. Hang on, axial stress. Let's just write it again. Da, 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 da. Meter squared. And now the x-axis is going to be axial strain. And that has no units, so I'll just put a dash here, meaning I've thought about this, but it doesn't have any units. Now, why is this not working? Because I think, let's make it be auto, the range here. There. Now I'm making it automatically decide what values to use for the axes to sample within, and it's now going to use whatever makes it work with that history. So let's see if this is so far making sense. Notice axial stress, plat sig Y, 0, 0, 0, 0, 0, and now it starts getting positive. That seems to make sense, but this axial strain, remember, we are asking for the Y displacement and dividing it by the height. The Y displacement is negative in this system. So we need to reverse the x-axis. So we go to, how do we do this? We go to the same history plot item, and it says versus XY. I'm going to click reversed. Holy smokes. Now I think we got it. So let's just make the x-axis 0, the minimum. And now we're actually plotting what we want to be plotting. Now we're plotting the axial stress versus the axial strain. Let's take a quick thing. Now that's got this crazy axial strain of 0.37 till it did anything. That probably makes sense because this is about 37% of whatever that height is, right? So, and we're not going to worry, right? We could adjust this. You could do a bunch of things. You could make the wall be closer and then start doing this. And so, but this is the reference, right? So here we go as we're applying the strain. So let's take a break. So the first thing, is everybody with me? This should all make sense. I think you've all been going along with me, right? So notice we've just done freaking crazy generalized things, right? Because if you understand this, these fish functions could be anything, right? These could be that crazy clay porosity mass. It's just a clay porosity mass, and you want to plot that versus time. Here you go. You use the history mechanism. You make a fish function, use the history mechanism, right? So this is the basic thing, and now we're going to go and continue on with this, and it's going to be your challenge to figure out, let's see if we can now choose properties so that we can get this curve. Okay, that's what we're going to do after our little break here. So let's do, let's see, new slide blank at here. Right there, this is the name of the game. Let's see if we can get this curve. And let's try to figure out what's causing the curve to exhibit the characteristics it does. Okay. So first, let me just show you a programming thing. Here we go. Here's the functions that we wrote to look at. Here's how we get axial stress. Whoops, and I didn't comment. I should have said what this epsilon y is. Axial strain, positive is contracting. That's why we had to flip the sign. Okay. Notice this guy here. Okay, so first of all, what's this doing? Why are we doing this? Somebody tell me.
By the pointer.
Correct. It's finding the pointer and then it's using the pointer in the next line. Well, the pointer's never going to change in this system here. So this is actually just slowing things down every single time we make this command. We do this. So what we should do is we should just create a global variable and do it once. So I'm going to call this thing WP of the platen. Global equals wall.find of what platen, boom. So now I do this once, and now I'm just going to use that in here. And I can get rid of this so that things are going to run faster. Okay. So there we go. Now let's just make sure this still works. Here we go. Axial stress versus axial strain. Boom. She's loading up. Okay. Now, let's actually load this thing a little bit slower so that we can see, because we're really going really, really fast. So let's go and just change this. So I don't know, let's do cycle 5, 6,000. And now make the velocity slower. So we're still going to use pvel as a reference, but now we're going to say 0.2, a lot slower, 0.2 times pvel. And then we're going to cycle again. So it's 1,000 more, but we got 5 times, so let's do 5,000 more. Let's just watch this one. I want to be able to zero in more closely on what's happening as this thing begins to get loaded. Okay, so now watch, it's going to go slower. Now it's going a lot slower. You can see it. It's pretty bumpy because there's not a lot of grains in this system. Okay, good enough. Still, I don't quite want to go that far. Let's go a little last 5 to 8. There, good enough. Okay, while that's running, let's look at this guy. I want to just get this guy. Okay. Want to make it bigger. There. And this is just a snapshot, I think. Yeah, there we go. Okay, this is what we're concerned with. Now, let's actually look at the numbers here and see if we can get in the relative range of this thing, first of all. Okay, so what's our system right now with the current values that we have? So let's get rid of this. There we go, stress versus strain. So let's just first dump this out to a file, to a bitmap, call it F1. And then I'm going to say, go to F1, throw it in here. Here we go. So let's try to compare these things. Let's get rid of that. I've never done this, so this is going to be exciting. I don't know what to expect here. Let's make that a little bigger. There we go. Okay, what are the units here? So we got stress in pascals. And is this AOT? Is this your curve?
Yes.
And so AOT has stress in megapascals. So what is this? So she's got, and how much strain? So the thing gets stiffened up after about 7% strain. And our strain, 7%. So that's 7,000. Okay, so let's just use this point right here and for now. So at this point, because ours is already stiffened up with this, let's just look at this slope here to begin with. Do we have the same slope? So her value here is 20 MPa, which is what? 20 times 10 to the 6, which is 2 times 10 to the 7. Do you agree? Am I right? 2E7 newtons per square meter. Is that what this is?
Yes.
Okay. So our game here is to be able to load our thing and get to this. So we're only at like 1E4. So we need to make this thing 1,000 times what? What do we have to change in our properties? That's going to, what is it that's going to affect? So the slope of this curve is like a measure of the stiffness of the overall assembly. And so think of it, we're in the process of applying this much strain, and let's actually apply a little bit more strain here. Let's go at the, well, I don't know, I don't want to apply a lot because this system is so badly, there's not enough particles. Yeah, let's go a little bit farther. I'm just continuing to cycle, right? And you can see it's pressing because we haven't changed anything. Yeah, and it looks like it's getting pretty linear here. And there's not much going on. Yeah, look, it's just linear. Look, it's getting bigger and bigger, and it's got a constant slope. Do you agree? See,
Yes.
y-axis is getting bigger, constant slope. Okay, before we start screwing around with matching that curve, the first question is, so that was 3, just a second. So I did an extra 3, I think. So while this is running, this curve is getting steeper slope. And as I mentioned, the slope of this is a measure of the stiffness of the system. And so what we're seeing here is when it's not touching at all, it has 0 stiffness, right? And here it's slowly getting stiffer until now the slope is constant, right? Slope is constant, measure of the stiffness. Make it red, make it bigger, boom, boom. So slope, first of all, slope is measure of stiffness of assembly, right? This is a macro measurement of the whole entire system, right? So slope, make it red, red and red. First of all, what is this slope? What is the slope called? Does anybody know the slope of this thing? What if this was a UCS test? What would the slope be if we plot axial stress for? If this was a UCS test, what would the slope be? There's a property.
Elastic modulus.
Exactly. So if this was a UCS test, axial stress versus axial strain for those boundary conditions, which is UCS boundary conditions, is a measure of the Young's modulus, which we typically use capital E to denote. Okay. In this test, we have different boundary conditions because we have sidewalls which are not moving. In the UCS test, it's free to expand. So therefore, this is not a measure of Young. This is not Young's modulus. And I think AYOT knows this. What is the name of this slope?
Constraint modulus.
Haha. So it's called the constrained modulus. I guess that makes sense. It's constrained. It's not just free to expand. So this is a, and what's the symbol they use?
Capital M.
Sorry?
Capital M.
Capital N, like that?
M.
M?
Yes.
Got it. Okay. So this slope is the constrained modulus. So, and our constrained modulus is a whole hell of a lot smaller, right? Let's just do a quick estimate of this here. It's basically M equals, come on, I'm firing up this math type thing. M equals, this is also a helpful thing to see what I can do with these plots. This is what I will do, right? So I can just use the plot directly out of PFC. So it's the change in Y over the change in X, right? So the change in Y here, let's just do it carefully. Whoops, let's not do that. I want this guy. Change in Y is this. So the change in Y is 1, 2, 3, 4. It's 0.4 e to the negative. That's a change in X. 0.4 e to the negative 1 times 10 to the minus 1. And that's dimensionless. And this guy is changing from 0. No, it's changing, let's say, from here. 0.3, 1.8. So it's like 1.8 minus 0.3 times 10 to the 4. Do you guys agree? 1.8, and this value here is, because that's where we're getting this. Well, let's just go. Sorry, let's just do it this way. It's easier. Let's just pretend it goes to, let's just make that, it's just this slope. So let's run that all the way to 0. There. So change UI. So then it's like 1.8 times 10 to the 4. Let's get that better. Here we go. 1.8. There. Okay, who's got a calculator? I bet you guys don't even own calculators, do you? Because you're young people. Do you guys have calculators?
We do have Casio calculators.
You do? Okay, who's faster than me? I'm trying to get my calculator right now. I have the same calculator that I got when I was an undergraduate. Like, it's about like 59 million years ago. And I still have it. Let's see. Who can do it? I'm going to do it. See if anyone else can do it. 1.8 e to the 4, enter.
450 kilopascal.
So give me a times 10 to the something.
5.
Okay, units, we screwed up here. We didn't put the units here. Style, text. These are in pascals, right? That's what stress is.
Yeah.
Newtons per square meter. So that means this is also units of pascals. And M target, do you remember? What's our target here? Just a second. Solid fill, white, boom. I want the slope of this. What we got here? I'm just gonna eyeball it here. Let's call this M star equals. It's gonna be easier to actually have a number here. It's fun. Often we screw around with models, but we don't actually put numbers in. It's very helpful to get a feel for these kind of systems. What do we got? What's the y-axis? Change in stress in this system. Let's go from here. Let's do this. Let's go from there to here. So change in stress is 30 MPa. 30 times 10 to the 6, right? And change in strain on this guy, help me, what is it, Ayat? 0.14 to 0.05, close enough. So that's, what do we got? 0.09. Point 0.09. So let's run this through the computation machine. I do it as well. Tell me what you get if you get the same thing as me.
Yes.
10 to the 8th.
3.3. Yes, I got the same.
Okay, 3.3. So the game now is to say, is it possible for us to change our model so that it has this same curve? And this curve comes from a real thing, which is this stuff that Ayat's going to tell us more about right here. These proppant beads, right? So that's actually the constrained modulus of proppant beads. What are we going to do to our model, guys? What can we change? What are the properties that the model has?
Kn, Ks, and friction coefficient.
Got it. Okay. And this is like the simplest type of granular model you could have. You have to have a normal and shear stiffness, because real materials do when you push them together. Remember when I pushed on my hand and moved my finger back and forth? So first of all, is the friction coefficient going to have much of an effect? What do you think?
It does, but not up to that amount of change that we need.
Okay. So what's going to be the main parameter that's going to control the stiffness of this system?
Kn.
Do you guys agree?
Yes.
Very Kn. What about Ks? What should we do with it? Think of it this way, and let's say fric equals constant. We got 3 parameters here. So, you know, in general, this is a nonlinear optimization problem, right? You could frickin' run some crazy nonlinear thing and look at the whole entire parameter space, right? You know what I mean by parameter space? It means all possible results that could happen with the entire possible range of values of all these 3 things. But we're going to use our physical intuition to try to figure this out. So part of the intuition was, well, friction probably not going to matter. We're going to match it. Then this is what you do with these things. Then you can change it after we get something, and we can see and verify that it really didn't matter. So we'll start with it being constant and equal to 0.5. Probably don't want to make it frictionless. Let's just make it kind of a real number. And what we got 2 variables now. And so what are we going to do? In order to turn this into one thing, let's call this K star. K star is going to be the ratio of Kn to Ks. And let's keep that constant. Are you with me?
Yes.
Does this make sense? So if we
Yes.
multiply Kn by 10, we're going to also multiply Ks by 10, because it turns out that in these systems, the ratio of Kn to Ks actually is a very important thing and has a big impact on stuff, which we'll talk about much later. So as our first attempt to do this, let's just do this. And now let's think about, if we want to get a 3 order of magnitude increase in our M, what do you think we're going to have to do with Kn? Double it?
Yes.
Just double
Start
it?
with double. Start with
Okay.
doubling.
Start with doubling, get a feel. Okay. You could kind of, well, let's do that and see what happens. Okay, let's double KN. So let's go to our data file. Let's where we created. Now we got to go all the way back to make the whole packing and everything because the packing itself is affected by all this. So here's our, I'm going to do a copy and paste. I'm going to comment out the previous values. So if I double KN and I keep the ratio of KN, KS the same, I double KS. You agree?
Yes.
Okay, so let's look what happens. So now it's just doing that packing. And there's no platen yet. And so we got to wait till it gets to equilibrium. So at this point, we're not monitoring, we're not measuring anything. We're just looking at the overall system behavior, right? That's why we do these tests, right? Because then we're going to start actually measuring some kind of quantity. What is that constrained modulus used for, in real soil? Do you know?
Not really. I didn't test soil, to be honest, to see what's the difference that I'm gonna get. But
No. Okay.
but as far as I get to it now, it's give you a feel of the compressibility of the soil.
Okay, so this is a test that's done in the real world to try to get an idea of the compressibility of the soil, which then I assume is an important thing that affects
Yes.
other things.
Yeah, especially for foundation engineering.
Now, first of all, what are we seeing here? It's freaking taking forever, and it's not really going as far. Like in the other one, after I cycled 11,000, I was already really close to the top. And this time, I didn't get as far. But let's see. So why is this? So now I ran the same number of steps as before, but I didn't even get to I didn't go down as much displacement, but I have the same velocity of the wall, but I didn't go as far. Why? Ooh, come on, you guys know the answer to this. What's the displacement of the wall is equal to the velocity of the wall times what?
Mechanical time.
Mechanical time. And so every time step, there's a time, every cycle, there's a time step. We take that velocity times the time step. That's the amount of motion. That's the displacement that the wall does. Now this system, because it's stiffer, ends up having a smaller time step. And so that means if we take the same number of cycles with the smaller time step and the same velocity, we're not going to go as far. You with me?
Yes.
Okay. Okay, that's kind of interesting. So let's just screw around here. Let's just cycle it some more till we can measure a slope. Ta-da. You can see the y-axis getting bigger and bigger. And it's hardly got any contacts yet. That's why this is bouncing up and down. Let's actually make this colored red so we can see it better. It's definitely going up. That's good. Just like before. And once it kind of gets more packed together, it's probably not going to be bouncing up and down anymore. Like now the contacts with the wall, they're not going to change for a while. And there's not really much rearrangement going on inside anymore. So it's kind of like a linear system now. It's the rearrangements that are causing all kinds of changes to this curve, right? So now let's stop. It looks like it's linear now. So we've probably gone far enough. Let's make a plot of this guy. And let's actually change this. No, let's not do it. Let's just do it this way. Okay, bitmap F2. Go back to this. Duplicate the slide, get rid of this. That's not what I wanted. I want to suck in that bitmap. And here it is. Da-da-da. Just a second. Let's crop this thing there a little better. So, what did we get now? Let's see if we could just use these same ones here. Da-da-da. Bring to front. Bring send to back. There we go. Let's make this thing blue. There, that's kind of the slope, right? I think I got the slope there. Little bit of a change there. Good enough. So, change in stress. Instead of, now it's 5 times 10 to the 4. So instead of 1.8, basically 5 times 10 to the 4, and the strain is probably about the same. Yeah, 0.4 times 10 to the negative 1. So what does this come to be? 5e to the 4 divided by 0.4 e to the minus 1. What do we get, Ayad? I get 1.3.
12.4. Yeah.
And let's do it in terms of 10 to the 5 so we can compare. So it's 13 times 10 to the 5, right? Because 13 times 10 to the 5 is 1.3 times 10 to the, yeah. So the difference, if I keep swapping back, so it went from 4.5 E5 to 13. Almost a little more than doubling. Okay, so what did we get? Double KN. The result was almost, I don't know, let's say 2.5 times M. With me?
Yes.
Makes
Yes.
sense? So think about this system now. And from what we've seen, these KNs, those are springs in here. Okay. And what we're doing now is measuring the overall stiffness of all those springs getting pushed. And just think, if I went now and replaced those springs, kept them all the same locations, but all I did was put springs that were twice as stiff, the overall result is probably going to be a curve and stuff that's about twice as stiff. That's kind of what we saw here, right? So given this, what do you think we have to do to the stiffness to make it 1,000 times stiffer? Because that's the modulus difference. So it seems like this K, right? If you double K, you double M. If you multiply K by 10, you probably multiply M by 10. So if we want to get M 1,000 times bigger, what are we going to do with K?
1,000
Increase
times.
it by 100?
Well, about like 1,000. It
Yeah.
seems like it's like a linear relationship, sort of. We don't got to, if we do it 2 times, we get, you know, we could work out this ratio, right? Of 4.5 and 13. What is that ratio? 13 over 4.5. 4.5. Assume it's the same. It's about 3. So let's do it by 100, and we should get a heck of a lot closer. Okay? Are we okay with that?
Okay. Yeah.
Let's do 100. And I
Yeah.
haven't done this. Now this is going to be a little bit of a pain, and you tell me why. So instead of 2E6, it's going to be 2E8 for both KN and KS. And now I'm going to run it. That didn't work. Let's do all. Here we go. And now, so first of all, what are we noticing here? It's taking a lot longer to do the computation. Why is it taking longer to do the computation?
It's stiffer and a smaller time step.
Smaller time step. Let's actually see what that is. Here's the time step. See, it's changing a little bit, but it's approximately 3, right there, 3 e to the minus 5. So 3, remember that. Here's the one we were running. It's 3e to the negative 4. Okay. So the time step got 10 times smaller because the stiffness got 100 times bigger. And the time step is proportional to mass over stiffness, the square root. So we take the square root of 1 over 100, we get 1 over 10. And that's why the time step is 10 times smaller for 100 times bigger Kn.
Yeah.
This is also why, as I was teaching you all this stuff, I was screwing around with this ridiculously soft system because it runs fast. But now we look and we say, oh, when we quantifiably look at this and compare it to a propant, and that propant is probably pretty similar to like a sand or something, it's actually a realistic granular material. It's much, much stiffer. So we have to make our model stiffer as well. But of course, it's going to take longer now to come to this equilibrium thing, right? In fact, it's going to take 10 times longer to run because the time step is 10 times smaller. So it's going to take 10 times more cycles. We're sitting here at 20,000. This thing was already done before, right? We'll just do this and we'll look at the effect, and I think we'll get the idea. And then I'm going to ask something else. While we're looking at this, I can tell you about granular systems with DEM, which none of you are going to really be looking at. But when people do granular flow modeling, like they have a bin filled with rice grains and they want to see how it flows, but if they change the shape of the bin, how does it affect the flow? For that type of model that's asking that type of question, it turns out that the stiffnesses of the particles have very little impact on the flow characteristics of the material. And so therefore, usually when people build granular models, they make the stiffnesses really, really low, unrealistic, but they don't care because they're going to get the right answer anyways, and the models run faster. Okay. And if you're going to do that and you're going to have a gravity-packed system, the thing that you have to worry about is the amount of overlap at every contact. If you have the same amount of load, think of this system, it's a gravity-packed material. So the total weight of the material is pretty much what's going to be acting on that bottom of the box. And remember, it's not exactly the total weight because there's friction and some of the load gets transferred to the walls, but approximately the total weight. And so that weight is going to produce forces down here, and those forces are going to be pushing against the spring. And so if the spring is very soft for the same force, you're going to get bigger overlap. Because in that granular system, the force on the bottom balls is always going to be the weight of the material. So if you just screw around and keep reducing stiffness, it's going to have bigger and bigger overlaps. And so the thing that controls then how soft you can make it is you got to make sure that overlap, maybe it's like 5% of the disk diameter or something. And so that's a very typical thing. And in fact, in these systems here that I recently developed for this oil company in Thailand, that's what we do. We set the stiffness as very, very small stiffness, and we make sure the overlap is not too big, and then we run all our models like that. So we can run these types of models very fast in like maybe 2-3 minutes. Okay, make sense? With me?
Yeah.
Yes. Yes.
Watch this, because this is
Yeah.
cool. This is cool. This is what I just did yesterday for this guy. Look at this. You're going to see a bunch of cool stuff about a DEM model. It's exactly the model I just showed. It's this. It's this sucker right here. That's what we're going to look at. Okay? Watch this. Sorry. Come on, PFC. I want the other one to come up. Yeah, it's gonna, oh yeah, it's gonna be a little slow because I just have one machine here. And here's the other PFC. Here we go. Cloud of particles dropping. It's still gonna go pretty fast. Watch this. Watch this thing bounce. It's like real sand. Watch this thing. Bounces up, right? I think this is really cool. Here's the force chains. There, this model has tons more particles than ours, but it's already going so fast. Now I put in layers, I color it, and now we push. And then the client came back and said, yeah, this is great, but I want to like change it. I want to do more than that. I want to be able to push it a while and then add more sand. So then there we go. We had the ability to make more sand. I'm going to drop that on there. Watch the entire system compress, right? Because of the momentum of that weight. Those are force chains building up, right? And the fact that it compressed that sand is kind of like a shock absorber. It didn't bounce. That new material didn't quite bounce as high. And now we're going to do the same thing. Once this gets to equilibrium, we're going to define new layers. And now we're going to go and push. And we're doing this in 3D as well. But again, notice the time step here, like 1e to the -4. That's what it was in our first system. Because that's about as small as you can do without getting too much overlap. All right. Any questions about this? No, it's done. So I think we're going to sit here forever. Let me just stop it now and say that it's close enough. And let's now save it as Gravity Pack, because now we're going to just run the test on it. Just a second. In PFC, you can select something and you can go to the magic button here that says just run that command. Whoops, yes. Model saved. Here we go. Odometer test. Let's run this sucker. This is probably going to be too slow as well. See, so now we're moving it. Oh, let's increase the velocity of the top wall. Does that make sense? Parameter 0.2. Let's do 10 times 0.2. And we can, oh, rats. Just a second. I don't want to run Gravity Pack again. So I need to call the my parameters again, because now it's going to have different values. Now I'm going to restore Gravity Pack. I'm going to recall this because now I'm going to set pval to that. Now I'm going to run this thing. There we go. That's probably reasonable. And I don't know if the number of cycles we took is enough. Let's see. Yeah, this is probably going to be okay. Although it's probably going to hammer that thing. Here we go. History. We'll just get this slope and see if it's 100 times bigger, like we thought. Oh, and then in this data file, I reduced, you can see it here, 0.2 times the flattened velocity because we wanted to make it slower. So let's just, I think it'll be good enough. This should go there pretty quick here. We'll just have to cycle a little more and we'll see what we get. And then I'm going to give you an assignment to make the next few steps on this. See, this is what happens when you do a lecture and you haven't actually done the thing yourself. But remember, I said I'm doing this as a test. I'm doing these lectures in this way because I think you're able to follow a lot better because I'm doing the same things that you would do as you're actually developing a model. So here we go, doing the same qualitative behavior, right? Let's just get this to be kind of not bouncing around much anymore so that it gets like nice and packed in there. Whoops, let's just keep cycling. Boom. So that's looking, there we go. Why is that curve now not bouncing around anymore? Someone tell me. What do you think is different? Why is this system not changing a lot?
No arrangement. It has been compacted.
It has, exactly. The force change, nothing's changing anymore for a while, right? Keep cycling. Look, nothing's really, there's no new contacts forming, right? There's no new stiffnesses getting put in there, no new springs. This is why the real test and this test has this stiffening effect. Okay, let's see. This is exciting. See what we're going to get. F3. Now, help me. Ah, there it is. This one, that's the first one. Duplicate, get rid of this. And we did 100 times Kn. And let's see what we get. F3. Crop this guy. All right, let's do this calculation. Send to back. All right, make that blue. Let's see. Try to line it up. There. That's about lined up. This is the 0 point there. That's the point there. So the x-axis, 1, 2, 3, 4, same thing. Notice here, this is the one we're trying to do. So 0.4, 10 to the negative 1, that's the same, but now the value of the stress is 4.5 E6. It used to be 1 point, so 4.5, and it's E6, just like we expected. And now AI. See, AI's doing this without even using a calculator. She's pretty amazing. Oh, I did it wrong. Just a second. 4.5 E6, 0.4 E to the 1. I hope you don't mind that I'm teasing you, AI.
No, I'm fine. It's 113 megapascal. Oh yeah, okay. Yeah, you can do that.
Oh, look. So now we're getting in the ballpark here. Did I do that right? Is that what you have? 100? Yeah, 1.1 E to the 8.
Yes.
Enter 0.4 E to the 1G. Okay. So actually, to make this thing 1,000 times macroscopically stiffer, so far we've multiplied this by 100. So, you know, now it's like got to be 3 times more. We probably hit it by 300, and we might be probably there pretty close. So what have we found out? We found out that in this system with these parameters, the Kn clearly has a big impact on the slope. And then the next thing, if you wanted to really dig into this, now you would just vary Kn over Ks and then see what effect it had. And it might not have an effect on this slope. In fact, it probably won't, but it'll have effect on other things. So here is the thing I'd like you to do. And I'll send you this. I'll clean this up a little bit and send it to you. And I'll type it in here. Like it says, see notes, do this. What I'd like you to do, I'll just say in words here. Get this thing to match, or, you know, kind of close. And then run the test so you get this nice behavior. And let's just talk about this again. So this is a stiffening. Oh, first of all, get this close, run the test, run it up to the same thing now, get it up to 35 MPa, try to reproduce it, and then unload it and see if it unloads. See if it's reasonably the same. I have no idea. I believe it should be reasonable and give a reasonable match, because once we get the slope, right, the question is, because if we have the slope right, that means the strains and the stresses are pretty much, they should end up being the same pretty much. We should be able to get this curve. And then the question is now unload it and see what you get. Okay, that's the first part. And then the next part is, why is this stiffening? Is there something we could monitor, take a history of, that would somehow be the key thing that we could monitor that's controlling when this thing stops stiffening? So the clue is what Shihang said. Things are not really changing, right? It's packed. So what is it that we could be measuring that kind of is not going to change anymore once it gets all packed? What do you think? What quantity? Hey, what do you think?
I was
What could
thinking
we be
about
looking at?
particle orientation, but that's like too advanced for our model, I guess.
I don't think that matters a lot, but what about porosity?
Velocity? Okay.
That would be one thing. But I think there's an even easier thing, which is the number of contacts that every particle has. That's what we call coordination number. The coordination number, by definition, is the average number of contacts that every particle has. And so I think what's happening as it's stiffening is you're getting more and more contacts. And when you get a new contact, you get a new spring, which means you get more stiffness. That happens in reality, that happens in the model. And so you keep getting new contacts. Eventually, you're really not getting any more. It's not the number of contacts, the average number of contacts, each guy is not changing really anymore. You could see that when you ran it. You could see the force change. Nothing is changing. There's no new contacts forming. So I want you to measure the coordination number during the run, and I want you to make a history of coordination number versus axial strain. And we should, if that hypothesis is right, we make those plots right above each other. They're both versus axial strain, but this one is coordination number. You should see, just like this guy, that coordination number should increase and then eventually reach a flat value once this thing doesn't change anymore. Does that make sense? Okay. With me?
Yes.
Got the idea? And now how do you
Yeah.
going to get coordination number? Okay. So there's two ways to do this. You can use what's called the measurement logic in PFC. There's a measurement circle you can put in here, and you can ask the measurement circle to return to you the value of the coordination number. And let's just take a look at this quickly here. So it's PFC additional features measurement logic, measured quantities, coordination number. Here it is, average number of active contacts. And there's a fish function called measure.coordination number. Here we go. Get the measurement coordination number. It's just like the other one for the wall, except now we need a pointer to the measurement guy. And that's going to be same idea, measure.find. Okay. And there's a measure create here somewhere, a command. That's how you're going to create the measurement thing. And we did this earlier on in one of those earlier lectures. So that's what I would suggest that you do. So you go and you position, and you might want to go, this is such a crude model because there's really not very many particles, but maybe you want to make the particles a little bit, have a little more, make them a little smaller, but don't change anything else, right? But even with this, you should still get the idea. Put a measurement thing in here that fits in here, that's a little smaller than this is going to be when it's finally done. And then just get that, right? Do it exactly the same way as we did here. You're going to basically, instead of wall create, you're going to do measure create, right? And then you're going to do, make a fish function that returns it and then hook it into the history. Okay. So I'll write that in here with a few hints. And if you're, it would be good, like all these things, right? That's why we do exercises. Like it makes you really kind of, oh, do I really understand this? Because I'm sure you're following along the basic stuff. So that's what I'm going to suggest. I'll send you that stuff in the next hour here. And next time, we're going to continue with this, but now we're going to say, let's add some bonds. And we're going to start talking about how, as soon as you add bonds, you get a really, really fundamentally different behavior. And we'll talk about some of the things of how it's different. And we're going to add really simple bonds, and we'll go from there. Okay?
Yeah.
Sound like a plan?
Yeah.
Yes.
Okay. So, thank you for all your attention. We'll call lecture 7 to an end. And Shihan, get some sleep, man.
Yeah. Thank you.
Okay. All right.
Thank you.
Thanks, everybody. Talk to you next week.
Yeah.
See ya.
Bye.
Thank you, Doctor.
Yep.
Thank you.
Yep. You're welcome.
Bye, everybody.
All right. See you later. Gonna leave the
Bye-bye.